Я хочу передать слово нашему гостю. Dear Professor, the tribune is yours.
Good morning, gentlemen and ladies. It's my great pleasure that I present what we have done during these recent 10 years in our group based on this investigation of interaction mechanism between radionuclides and minerals in the geological disparity environment by using small-angle scattering techniques. Okay, I just start the first part. Here is what we are going to do in China and we are doing now. We are going to build a deep geological disposal for high-level radioactive waste. I think that in Russia you are doing similar things. You are planning to doing similar things. Okay, so but there are some interesting or important scientific problem that we are following. That is the migration of the radionuclides in the repository sites. The previous, the old idea or previous think is that these radionuclides were not going anywhere. Oh, sorry. But in recent studies show that the colloids of the minerals will absorb these radionuclides and transport them to the biological spheres. So it is not good for us, so we have to understand. So what we are doing in China during this recent 12 years, we are trying to understand the mechanism of radionuclides migration. We focus on these three topics. Firstly, intrinsic colloids, study the hydrolysis kinetics of these actinide radionuclides in the aquatic environments. And also we try to understand these pseudo-colloids, which means the clay colloids associated or absorbed with these radionuclides in the aquatic environment. Also, we are interested in this interface problem. We try to understand how these secondary minerals formed and their interaction with radionuclides. In the meantime, in the other side, we are trying to do some structural modification of these natural materials in order to enhance their absorption and retention capability of this actinide radionuclides. So I just give you a resume of what we have done. So if you're interested, we can discuss later in details. I might go a little bit quick because I have another PPT want to share with you. Here is what we are thinking. Because we know that this colloid system is under this mesoscale, but the previous study, they just focus on either macro scale or micro scale. There is not efficient in situ and accurate analytical methods to help us to understand what has what is going on in this mesoscale. Fortunately, we found this technique, small angle scattering, which is a quite powerful technique, can help us to understand this structure and a lot of in situ information, physical information in this mesoscale. And so we think it is an ideal method for us to understand the in situ and the mechanism of this colloidal system containing radionuclides. Also, we use this technique, we call it greasing insidious small angle scattering technique, which can help us to understand what is going on the surface. These two kind of technique are not new, but Before, we didn't see many literatures reporting the studies using these two techniques to do the study under this direction. So since 2013, we do something. Here I show you what we have done before. Here it is 18 months study using small angle scattering to invest the kinetic of the thorium-4 colloids in the occurrence system using the small angle scattering technique. Because we don't have qualification of the real radionuclides, so we choose thorium-4 as the represent element of the plutonium-4. And we using this large-scale facilities in Shanghai synchrotron facilities, we study what has going on since this 18 months. We see the signal change at the first day and 1 to 5 months, and at the end we stopped at 1.5 years. We see this structure change by using the analytical method and some modeling. We see how this intrinsic colloids change as a function of the time. So here is an example of the long time scale investigation and in situ studies. And I show you a very short time investigation of what has going on in the nitrate, uranium nitrate induced into Beisan underground water. Beisan is where China decided to build underground water and or high-level nuclear waste depository. So we took the real underground water from this place, and we see what is going on this uranium nitrate. And using this special devices, we can see in a very short time, beyond maybe within 1 minute, the structure changes from this uranium nitrate element. What is going on? We see this early stage of aggregation of verterite colloids and nanoparticles from forms of branched network structures with a mass fraction dimension of 2.1, and beyond 45 minutes, distinct aggregates with a characteristic size of 90 nanometers emerge, followed by the transformation into denser agglomerates over time. So here are two examples on the short time scale and the long time scale using small angle scattering. And also we try to understand what is going on, these radionuclides with geological particles. These are the nanoparticles that, or colloids that we got from the Chinese minerals. We call it Gaomiao's bentonite, and we study their structure in water using small angle scattering, and we compare them with the colloids and the bulk. We see their structural difference, and we also see what is going on as a function of the temperature, and also the association with different cation ions. And here, this is a real-time structure evolution patterns of the Gaomiao's bentonite colloids and the uranium composite system under different temperature. We can see that in the natural occurrence environment, interaction between bentonite and bentonite colloids and uranium hydrolysis product occurs primarily at bentonite surface, demonstrating no significant impact or on the interlayer structure. But with the increase in temperature, enhanced molecular Brown motion coupled with the presence of uranium hydrolysis products induce interference with interlayer structure characterization signals. And then I show you what we have done on this secondary minerals. We're using this grazing insidious small angle scattering to try to see what is going on the interface. Here we use vanadium and at that moment as another represent elements of plutonium, and we use the AFM and associate with G-SAX method to see their structure change. This give us some feasible results to give us good confidence to follow. This is just a starting point, and then we are going to prepare this uranium mineral films via pyrohydrolysis of uranium solution at the interface, and we study their interaction with light rare earth elements. So we are trying to form this uranium, we call it uranium UOH films, to simulate the spent nuclear fuel underground interface, and we invest this phase composition, morphology, thermal stability, and other information used in grazing angle X-ray scattering associated with other techniques. So this is what we see, and in order to save our time, I don't read all of this. This study reveals that this UOH primarily absorb REE via on the ion exchange and the structure incorporation, where this element is only retained through surface physical absorption. And this film exhibits selective absorption for high charge and large ratios ions. And this phase, we call it midascopic phase, a corrosion product of spent nuclear fuel, can structurally accommodate flowing ions. However, but these ions, with its low charge to ratio struggles to enter this crystal lattice. As a natural barrier of the retarding radionuclide migration, this phase demonstrates significant retention efficiency, particularly for the REE-like radionuclides. But this finding provides critical experiment insights to evaluating the performance of high-level radionuclide waste repositories and designing engineering barrier systems. So there is another recent study. We use the same system, but we study what is going on as a function of time using the similar method. I will not spend too much time on this. The last part is the structure modification of the natural materials and in order to enhance their absorption, retention capability, and reduce their colloidal transport probability. This is what we do. This method is not new. We just pillared this bentonite. This bentonite is from China. Is to aim to use as a barrier of the dispository. We call it Gamiao's bentonite, and we pillared this bentonite using aluminum inorganic polymers, and we're using small angle neutron scattering to reveal their retention ability of the water to see if water can go inside into this different place. And we also do some real plutonium absorption experiment to compare their absorption capability before and after or a structure modification. And of course, we see this significant improvement. These are the seminar work, so I won't spend too much time of our previous this occasion. You see, as a summary, over these past 12 years, our team has conducted primary investigations into these four research directions. From the fundamental research and academic perspectives, we have undertaken exploratory studies addressing colloidal immigration and radionuclide retention, retardation mechanism relevant to deep geological dispersion of radioactive waste. In the future, we aim to align our research more closely with the practical engineering conditions and operational requirements of the Beishan. Beishan is where we are going to do this in China. Beishan Underground Research Laboratory. This strategic shift will enable us to conduct more targeted investigations encompass both applied basic research and the practical engineering applications. I show you what we have done. I tell you a small story why we do this. Firstly, we designed this structure-changed minerals, and it shows remarkable absorption capability for these radionuclides. And then I created a company in 2018, and I tried to sell this product to the Chinese industrial customers. Unfortunately, when I showed them this product, they said, okay, this is looks good, but we won't use such materials in the point of industrial application. And I was quite depressed, but I want to know why. I asked them, so if you don't want to use our structure changed materials, what you are going to use, or what you are using for your daily work? So they show us some design. They show me some following products. They say that if you can make homemade, not foreign product, we are glad to try this. So since 2018, during 6 years, I also did a lot of work on these studies and applications on this high efficient extraction and separation materials for radionuclides. And the aim is to industrial application, not just stays in the lab. Since you are all the experts of this area, I will not spend too much time on this basic introduction. I just show you. This is one exciting or interested what is going on in China. I think that is the same, similar in Russia. Is radionuclides related, for medical application. So in China, we are trying to build a whole industry which can supply our own, radionuclides for the medical application. From the different source of this perspective, we all face the same problem. These are the general 3 types of the methods that we can produce radionuclides, we have to face this problem. Either different paths you choose, how can mixed radionuclides be separated and extracted? We choose, there are many different ways to do this, but we choose extraction way because for many reasons it can be, expanded in the industrial way. These are the market investigation. Just in China, we have a big demand on this type of materials. So this is a good encourage for us. So here is our principle, the core principle to do this. We just, it's not mysterious. We just design the different chelators, and we immobilize these chelators on the resin structure. So you can see into the different type of the elements, we can choose or we can synthesize different molecules to do this. But the very important thing is that we can produce these different molecules from kilogram level to to from gram level to kilogram level and even to the ton level, using a very considerable cost. So it gave us a chance to go into the real application. Oh, it can work. Please have a
Academician Yang Minhao's team, extraction resin. Extraction resin is a spherical polymer containing organic extractants. It forms a macroporous structure composed of polymer chains, capillary pores, counterions, hydrated ions, limiting ions, and functional groups. Through selective coordination by functional groups, pore size sieving, and synergistic effects of intermolecular forces, including van der Waals forces and hydrogen bonds, it achieves selective adsorption and solidification of radioactive elements. This material demonstrates high target selectivity in strongly acidic environments for element extraction, followed by efficient release in weakly acidic or neutral conditions, enabling effective separation. Widely applied in radioactive isotope extraction, high-level waste treatment, and environmental monitoring. Academician Yang Minhao's team, extraction resin technology. This fully domestically developed and self-controlled technology encompasses extractants, resin backbones, raw materials, synthesis processes, and mass production, breaking foreign monopolies on core technologies. The resin's extractant loading capacity reaches 40 to 50%, resulting in superior extraction efficiency. Moreover, its unique production process and original macroporous products specifically address industrial requirements. With strong customized synthesis capabilities, the technology provides complete process solutions tailored to clients' specialized needs.
So if you are using similar product from France called Triscam, so here is a good replacement of Triscam. We gave even better performance, but much lower cost. We have already started our application in China since this hard working during 6 to 5 years. Here are the different, we can almost replace all their series of products. And also for the uranium separation, we can provide industrial level product. I show you what we have done, on this strontium-specific absorption resin. It is not mysterious of these molecules. We call this core function group. This is 18 cron 6, but it is very hard to synthesis. You can see we are the only Chinese production line in China. We can provide more than 100 kilogram scale capability. We are the only one in China. So this resin is quite expensive from a French company, Triscam. But if you came to us, you can see our performance is better than them, and our price is much lower than them. This is another resin, and this is much cheaper, and again, our performance is much better than the French product. This is another type of things dealing with organic solvent, radioactive organic solvent. This is try to replace the American product, which calls NOCHA. Also, we have a very good performance compared with the American product. Oh, and this I just do it quickly because you are all the experts. You know exactly how this product can be used for application area. These are some real application examples we have done. We use DGA resin to remove plutonium and other elements, and also some uranium-specific absorption resin to help the uranium industry. And also, this is a good product, can do the monitoring of the environment sample. You know that. This is what we are going to do, or we are doing for the moment. We focused on this targeted alpha therapy technology, and we focus on this RA223, sorry, I forgot their English name, and this PB212. And we are trying to give same Chinese replacement compared with a foreign product, with much better performance and a lower price. This is what we do for the PB, and our domestic product shows good performance compared with the French product, and this is for the radium, but we are still progressing this. It is not yet finished. Just to show you what we are doing. And at the end, I show you what is our team. This is a state key lab for the environment-friendly energy materials. We located in Sichuan province and in Mianyang city. Mianyang is the only science and technology city of China. So you are all welcome to visit our city and our lab. So you see, we focus on these 4 directions: the fusion, fission, energy, materials for nuclear waste treatment and disposal. This is where our team are, and other 2 directions not related with nuclear direction. This is our team. We are international team. So this is Mark Henderson, the Australian professor. I met him in France. I spent 10 years in France before I come back to China. So this is Laszlo, the Hungarian large-scale facility scientist who is expert of small-angle neutron scattering. This is the Pakistan postdocs. So this is our foreign team. We are trying to do such things which I presented just now. So thank you for your attention. Here is just a brief presentation of what we have done. Thank you.
Пожалуйста, вопросы. Да, Наталья Сергеевна.
Thank you for your presentation. It's very impressive and very interesting.
Thank you.
My question is, I have 2 questions.
Yes.
What is the percent of nuclear energy that China currently uses? What is the percent, like 10%, 20% of all the energy?
Oh yes. We are, because of the Fukushima accident, we shut down the development of the plant for over 10 years. But since 2022, you can see the government obviously accelerates this nuclear project. Now it is about 5 to 7%, but already the number of the plants we are constructing is more than American. So for sure, China will be the most, the biggest, the first nuclear energy country in the following years. So we are continue approving the plants. Now they are all around near the sea. But I heard that maybe in 5 years we are considering to build up the plants in the inner place.
I see, thank you. And my second question is, you have a lot of results, and our laboratory of radiochemistry has a lot of results as well. So what are your plans of collaboration with our laboratory of radiochemistry? Are you planning to apply for common grants for projects, or what are your plans of collaborations with our institute?
I think that we, of course, firstly, I want to establish the real collaboration with your institute based on these two directions, and apply common grounds and program, and exchange researchers and students. But you see, the competition is high. Not easy to get funding compared to before. So that we can, I strongly recommended that we can consider what I presented the last presentation. We may follow, we may start collaboration on this industrial aimed project. I believe that there are many institute or scientists in Russia are using TraceCam, the French product, but it is extremely expensive. And this high price stops many studies and stops even maybe some potential engineering project. But if we collaborate together, we can manufacture much better design or materials with much lower price. So many things can happen. And in this area, there are less competition. Not many, we are the only company in China group doing such replacement thing. And I think that there are not yet a French company or French group are doing this. So this area is quite, I think, quite a good direction that we can try.
Thank you very much.
Thank you.
And your international team is very impressive. So I think our mutual visits and collaboration may be beneficial for both sides. Thank you.
Yeah, thank you. Yeah.
Пожалуйста, да, Петр Сергеевич.
Thank you very much indeed for your presentations. If I'm not mistaken, you have applied an impressive set of complementary analytical methods to studies on colloidal migration and absorption of radionuclides onto clay, including modified clay minerals. And would you please clarify, radionuclides may be absorbed onto clay minerals. In which species can be absorbed? Dissolved species or colloidal particles as well?
Can you please repeat? I don't understand. Sorry.
I'm sorry. You have studied the absorption of radionuclides onto clay minerals. And to your opinion, which species are absorbed onto minerals? Soluble, dissolved, ionic forms, or colloidal particles as well?
Oh, okay. Thank you. I understand what is your questions. I think in both these soluble species more, I think, like surface absorption, or they go into the interlayer structure. But for this hydrolysis, the bigger particles, they may just absorb or precipitate on the surface of these minerals because they are bigger. That's why I presented quite quickly. One of our work is we are trying to design a bigger pores, macroscopic bigger pores structure change the minerals so that it can contain the bigger polymers inside. Here is my question, my answer. Yes.
Пожалуйста, еще вопросы. Да, Лидия Николаевна.
Your presentation is very interesting for us.
Thank you.
Can you tell us, have you found fractionation of uranium and thorium in colloidal system, or they never fractionate? Because in carbonate magmatic system, uranium and thorium, they together until the very late stage hydrothermal process. when uranium became 6 valency. And at that stage, of course, fractionation between uranium and thorium very great. But in colloidal system, do you have fractionation, so separation of uranium and thorium, or they always together?
Thank you for your questions. We haven't seen such fractionation of these particles. For both thorium and uranium, we all see this agglomeration. They become denser and denser. But maybe our observation time is not long enough. You see, one is 1.5 years and another is just 1 minute. Maybe we can try to see what is going on for a longer time. Either they will do such kind of conversion from denser and denser to the looser and the looser.
But in a very acid media, which you showed us, the uranium and thorium always together, because uranium in 4 valency, but never 6.
Yes, but
in alkaline media, it will be another case.
yes, what we focus on for the exploratory background, we are not focusing too much on the acidic environment, because our Chinese underground water, the pH is between neutral to weakly occurs. 碱怎么说? No, from 7 to 8, the pH. So, or Chinese underground water. So we focus on that pH. The carbonate environment is very important. We know that, but we didn't do much kind of research before. This is what I showed as a summary, because before for this fundamental work, we think too much about academic point of view. We don't think too much practical point of view. So in the following, we will switch our attention to the more engineering and the more practical situation. So we may need your help and guidance in the future. Thank you. Yeah.
Thank you.
Пожалуйста, там.
Thank you for the very interesting talk. I would like to ask you how long the resin will serve in the process.
How long?
How long?
Yes.
How long the resin will serve?
Will absorb the how long?
For absorption.
Kinetics.
You mean resin or resin?
For resin. Yes.
Resins are quite fast. Resin are quite fast. We do some mechanism. They are from minutes, just maybe 10 to 30 minutes. They finish their absorption.
About how long time? I mean years. How many years the resin will serve in the whole process? Because radioactive process very damaging.
I don't understand. What is your question? Maybe you can ask in Russian, and my colleague help me to. I cannot understand.
Я хотела спросить, как долго будет служить эта смола? Вот. Много лет.
The question is about living time of resin. Living time of resin.
Lifetime.
Lifetime.
In fact, it depends on the different point of application aim. For example, if just for the environment monitoring, you just use it for environment samples, analytical process, it can just use once, then we should reject them. So, but this whole process lasts only maybe half days maximum, I think, or not more than 1 day. But some industrial customers, they use it to absorb the high level elements. In this case, it lasts 3 to 6 months maximally. Some of them ask us to give them the guide to reuse it, because this resin, normally they can reuse it. I mean, they absorb, they release, they absorb, they release. They can do this maximum 8 to 10 times without much loss of performance. But we nearly meet such demand, because the time will be very long. In the industrial level, maybe 6 months is the normal time. 6 months can work no problem.
Okay.
Very well. But for the longer time, we suggest our customers to change, to replace the new resin.
Okay. And other question, is there any possibility to implement your developments in Russian enterprises of disposal of radioactive waste?
Is there any probability?
To implement your technology, your methods to Russian enterprises?
To Russian?
Enterprises.
Russian
companies, okay.
Yes, we are glad to consider this. You mean we collaborate with Russian companies?
Yes.
Based on this resin stuff? Yes.
Thank you.
We are quite interested to do this. If you have a better idea, or better molecules, we can collaborate. You give us your idea how to design these molecules, and we in China we try to make it as a real product in the level of 100 kilograms or even bigger, with a considerable cost. Then we can try to recommend this product to the customers, not only in China, in Russia, maybe all around the world.
Thank you. Еще, пожалуйста, вопрос. Да, пожалуйста.
Thank you for interesting presentation. Do you study behavior of clay colloids in some fractures, or maybe with interactions these colloids with some surfaces of minerals from fractures, such as calcite, chloride, and others? Do you study the heterogeneous system when colloids will be migration in fractures when we dispose of this radioactive waste?
We haven't done this before, so that's why I think there is a lot of things need to be done in the future. We haven't done this before in the real transport. It's more like academic or in the lab.
Пожалуйста, еще вопросы есть. Можете по-русски задавать вопросы, если хотите. Да, пожалуйста.
Thank you for your presentation. Two short questions. One about your product. Do you have a resin for plutonium?
Plutonium?
Yeah.
Yes, we have.
Okay.
DGA is a good choice, but it depends on the conditions that you want to do.
Maybe I misheard it.
Yes.
Okay. And other question about synchrotron experiments. I saw there were experiments in situ, right, with uranium.
Yes.
How long does it experiment carried out?
How long these experiments take?
Take out, yeah.
You know that uranium experiment is very short, very short. We design a mix system, and the beam just goes through this mix chamber, and the measuring time is 50 milliseconds per sample.
Пожалуйста. I have a question.
Yes, sir.
Question. You showed us a picture and wrote core functional groups.
Yes.
What is the role of functional group in the center of the bead of resin?
What is the role of the function group?
In the center of the bead of resin.
In fact, this function group, we use a coordination chemistry. It's just, you know, this coordination chemistry, this function group can absorb, can extract with high selectivity to these elements, radionuclides. Why we use resin? Because normally in the room temperature, most of these function groups, they are in the liquid form. They are not in the solid form. So either in the industry of nuclear industry, either they do the liquid extraction, means you resolve, you put this ligand, this group in organic solvent, and you mix them with the liquid, the aqueous, you know, water containing radionuclides. You do the liquid extraction. Or another way is to immobilize this resin on the immobilize this function group on the resin to do the liquid solid extraction. So these two methods has its own advantages, but in the practical application, especially for the environment sample monitoring, most of customers, they prefer to use this, you know, resin containing function groups. They just put them in a chromatographic tube, and they just go through the samples. Then the elements that you want to select will stay in this resin in the tube. Then you use another kind of way to release, to rewash them. It can be in the point of manipulation, it can be easily done. That's why we use resin. It's just for that. Resin is a very highly porous structure, so that when the liquids containing radionuclides, when they go through, they can have enough, you know, or maximum contact with these groups staying inside the bond of this resin. That is the only way. We can also use directly these function groups, but it depends on the real situation.
Thank you. Есть еще вопросы? Thank you very much.
Thank you for your attention.
Сергей Евгеньевич, я хотел вас попросить пару минут рассказать, в чем вы думаете будет коллаборация, какие пути будут коллаборации, что вы намечаете?
Для начала хочется еще раз поблагодарить профессора Янь Миньхао за его интересный доклад. Значит, небольшое тогда введение. Собственно, профессор уже упоминал, что Китай крупнейшая ядерная держава с развивающейся атомной энергетикой, очень большими шагами, и учитывая их, конечно, промышленность, да, на каком уровне находится, без этого, соответственно, необходимо. То же самое происходит сейчас и в России, и в ближайшие 20 лет мы должны получить уже в России новые мощности по по новым, во-первых, реакторам на новой технологической платформе, которые будут совмещать привычные всем уже реактора на тепловых нейтронах, где делящимся компонентом является плутоний-239, собственно, что явилось основной целью исследования наших гостей. Наши новые реактора будут уже сжигать в том числе и плутоний, поэтому определенные тут, так сказать, проблемы, которые связаны с миграцией плутония в окружающей среде, в будущем будут минимизированы. Но тем не менее, период полураспада плутония 21,5 тысяч лет, поэтому понимаете, что то, что уже есть, это хватит на многие-многие поколения исследований, и учитывая его высокотоксичность, как бы от этой проблемы никак не избежать. Упоминалось в докладе о стеклованных отходах, которые будут размещены под землю. Собственно, это та же самая проблема, что и у нас. Глубинных захоронений на самом деле еще в мире официально действующих не существует, в том числе и в Китае. В России на рубеже 40-х годов такое хранилище должно быть создано. Туда будут размещены остеклованные отходы, исторические, так сказать. Они, конечно, не такие опасные, как будут в будущем. Они уже выдержаны, то есть период полураспада цезия, стронция 30 лет. Ну вот считайте, с 70-х годов, собственно, уже нет, еще через 300 лет не станет, но сейчас, по крайней мере, в 4 раза упало. Это много. Вот. Но это, извините, такое введение небольшое. Это все к тому, что задачи, которые стоят перед радиохимией, перед радиоэкологами, они неизбежны и на многие-многие века даже вперед будут определять вот то, что произошло в 20 веке, то, что, собственно, перевело, по сути, жизнь человечества на другой уровень, конечно, влечет неминуемые проблемы, да, для будущих, но тем не менее. Наша задача решить это уже сейчас, не затягивая, чтобы не перекладывать, чтобы не было этих отложенных решений, чтобы не перекладывать все проблемы на будущее поколение. Известно, что, в частности, многозарядные плутоний, уран, америций, нептуний, это долгоживущие актиниды, могут существовать в различных условиях, в различных формах, поэтому определение форм их нахождения, по сути, определяет вообще выбор путей реабилитации загрязненных территорий, выбор путей их фиксации, в определенной, так сказать, зоне, да, потому что так или иначе все ядерные объекты находятся в зонах, которые, естественно, оборудованы множеством сотнями скважин, постоянно происходит мониторинг, это неизбежно. Но тем не менее, необходимость зафиксировать их в той зоне, это как бы достижимо, а с учетом развития новых физико-химических методов, которые, может быть, пока мы даже не все имеем в расположении, а китайские наши коллеги имеют. Поэтому я думаю, что здесь с точки зрения научной части, я думаю, что мы вполне можем соединить наши возможности работы с реальными радионуклидами, возможности китайских коллег по применению современных методов, вот уже, которые, собственно, развивают коллеги, малоуглового рассеяния, или которое упоминалось уже, основанные на методах синхротронного излучения, в частности, масса современных методов, по сути, позволяют переосмыслить поведение радионуклидов в окружающей среде. Ну и, конечно, глубинного захоронения, как бы не хотелось, избежать не удастся. Это задача будущего на десятки и сотни лет вперед. Вот. Что касается не научной, так сказать, взаимодействия, то мы это уже примерно обсуждали. Это, конечно, да, обмены вот в части аспирантского взаимодействия. Аспиранты — двигатель вообще науки всегда в мире, особенно мобильные. Так что здесь я согласен, да.
То, что мы говорим, у нас есть две замечательные переводчицы, доходит до сведения нашего гостя. Кто еще хотел бы выступить? Пару слов сказать. Тогда поблагодарим нашего гостя, профессора Миньхао. Thank you very much for your presentation. Yes. На этом мы давайте закончим заседание нашего ученого совета. Спасибо.